video, we are going to look at a case of uniformly accelerated motion and an example of uniformly accelerated motion that we talked about in the previous video. Uniformly accelerated motion is a motion in which the acceleration is constant and the acceleration is non-zero. Since the acceleration is constant, and acceleration by definition is the rate of change of velocity, the velocity keeps on changing. It changes. Okay. Free fall motion is a motion in which the acceleration is constant, which is actually equal to the acceleration of, it is an example of uniformly accelerated motion. It has a constant acceleration which is equal to the acceleration of free fall. This acceleration of free fall, it changes from planet to planet. Basically, Earth will have a certain value of acceleration of free fall. Moon will have a different value of acceleration of free fall. A different planet has a different value of acceleration of free fall. Earth has a fixed value of g equal to 9.81 meters per second squared, and you guys need to learn this. Acceleration of free fall on the Earth's surface is 9.81. Okay, now let's look at a few very important cases with respect to the exam. First case, a ball or any object being dropped from a certain height. This key term drop is important. Anything that is dropped means that its initial velocity u is always 0. Its initial velocity is 0. Since we are assuming that this ball is being dropped, this ball is falling on the Earth's surface, acceleration has a value equal to 9.81 meters per second squared, which is actually the acceleration of free fall of Earth. We can use a stopwatch to measure the time for the ball to reach the Earth's surface, and this height can also be measured. Okay, all these values that we've just measured or calculated, that we have acceleration of free fall is known, time is measured, height is also measured, initial velocity is known, the final velocity can be calculated from the equations of motion that we discussed in the previous videos. All the equations of motions are applicable. All equations of motion are applicable on free fall motion because this is a uniformly accelerated motion. For example, we need to find the height through which the ball has fallen. We know its initial velocity, we know the acceleration. If let's say a time is also given to be 10 seconds, we can calculate the height by using the formula S is equal to ut plus half at squared. S is the displacement, which is basically this height. So h is equal to u is 0, so this entire term becomes 0, plus half acceleration is going to be 9.81, and it's going to be positive because the ball, as it falls downward, its velocity, it increases. So whenever the velocity is increasing, the acceleration is positive. 9.81, and the time is 10 seconds, so 10 squared, and whatever answer that we get over here is going to be our height in meters. This is how we apply the equations of motions on free falling bodies. So this is the first scenario, the first case that we've done on free falling motion, free falling objects. And it is assumed that air resistance is negligible in this motion, because if air is present, then the acceleration will not be constant, and when acceleration is not constant, the equation of motion will not be applicable. Okay, so it's important that air resistance is negligible. Now let's look at the second case, in which a ball is thrown upwards from the Earth's surface with an initial velocity u. It reaches a maximum height h, where it becomes momentarily at rest. Then the ball starts falling in the opposite direction, and its speed increases in the opposite direction, and then again it reaches the Earth's surface in a total time t. Now, an important characteristic to note here is that when the ball is at the same height, the magnitude of the velocities in the upward direction and in the downward direction are equal. This is an important point. When the ball was thrown upwards, its magnitude was u. When the ball is returning to the Earth's surface and it reaches the same initial height, its magnitude is all still u, but the sign changes because velocity is a vector, and when the directions become opposite, the sign they flip. As the ball goes upwards, its speed decreases. This means that going upward, the acceleration is acting in the opposite direction to the velocity, due to which the velocity is decreasing. So this means that going upwards, the acceleration is negative. Reaching the maximum height, the velocity becomes zero because the ball is momentarily at rest. And then after reaching the maximum height, the ball then starts moving in the opposite direction and its speed starts increasing. Increase in speed would mean that the acceleration and the velocities are in the same direction now. And since the acceleration and velocities are in the same direction, this means that the acceleration in the coming down in falling is positive for this ball then. And finally, it reaches the Earth's surface. Again, height is given, time is given, velocity is initial and final are given, so equations of motion can be applied over here as well. Because acceleration, again, is equal to the acceleration of free fall, which is constant because we are assuming air resistance to be negligible, and for the Earth, it's 9.81 meters per second squared. Now let's look at a very interesting case. What if the ball is dropped and the timer isn't start immediately? Doesn't start immediately. In that case, let's say the examiner tells you that as the ball passes the first checkpoint at A, the person conducting the experiment, he starts the timer, and as the ball passes B, he stops the stopwatch. So the stopwatch starts at A and stops at B. So the time from A to B can be calculated to be t. And you are asked to find this distance in between A and B. In this case, the ball, although was dropped from up here, its initial velocity will not be considered to be zero, because the initial velocity of the ball is that velocity with which it passed the first checkpoint A, and that velocity is not gonna be zero. This is an important point to note because the ball has already gained some speed moving this upward distance above A. As the ball reaches A, its velocity, whatever the velocity is, let's say it's given to be 10 meters per second. We are gonna take that to be the initial velocity. Okay, so this is an important point, that whenever this term dropped is used, only dropped is used, so yeah, its initial velocity is zero. But when a case like this is given, that the timer starts after the ball has traveled some distance, then its initial velocity is not gonna be zero. So long, and one more thing, so long as the object falls On Earth, its acceleration is 9.81. If two bodies, okay, this is a very important point that I'm going to discuss right now, related to the free fall motion. If two bodies in vacuum, or if two bodies which are undergoing free fall motion are dropped from the same height in absence of air, so that air does not interfere and the acceleration remains constant, will reach the Earth's surface at the same time, or will reach the surface of any planet at the same time. Reason is because the two bodies have the same acceleration, which is 9.81 meters per second squared. So their speed will increase at the same rate, and they'll reach the Earth's surface at the same time. Okay, so if I have a leaf and a book or a block, a heavy block, and if they're both left dropped from the same height, they'll reach the Earth's surface at the same time. They both will hit the Earth's surface at the same time if air resistance is negligible at the same time. This is an important fact to remember, and the reason is simple, because the acceleration for both the bodies is constant, which is acceleration of free fall. Over here, I have 10 kg block and a 1000 kg block. If they are both the blocks, if dropped in vacuum from the same height, basically if vacuum means absence of air, right? So if they are dropped from the same height in absence of air and are allowed to fall freely, free fall would mean that they would again have the same acceleration, which is equal to the acceleration of free fall. They'll reach the ground at the same time regardless of their masses. They'll reach the Earth's surface at the same time, because the acceleration of both the blocks is gonna be equal, which is 9.81. Thank you.